Okay, so welcome back to this small session on teleportation. So in this session, we will work out the theory and circuit for teleportation and discuss what are its application. And then towards the end, I will have a quick lab session on this as well. So let me begin by sharing my screen. Okay, so teleportation is actually very important. Not, from the point of view of what happens in some sci-fi movies, but from the point of view of quantum computing. And the reason is this, that teleportation means that if we have a certain quantum mechanical system and it has some state psi, and suppose we want to transport the state of this quantum system to another system, and suppose that this is one physical system and this is another physical system. You can imagine that, okay, this is perhaps a state of a qubit uh, in one qubit or in one harmonic oscillator that we have physically implemented at one part of the circuit, and then this is another part of the circuit. Usually this quantum computer has a single chip on which we have multiple oscillators that are working as qubits. And so on. So far people only have planar chips, but maybe in future there could be distribution of these oscillators in 3D. But what happens that they have provided the functionality, for example, for controlled operation between these qubits by having some oscillators between some of the qubits. So maybe there's coupling, physical coupling available between this qubit and this qubit and so on. But your algorithm requires maybe some operation, controlled operation between these two qubits, but perhaps after some time you want to have a controlled operation between this and this qubit. So that is somewhere in your algorithm and so on. So there may not be the physical possibility of performing controlled operation between this and this. So what happens is that the quantum computer can transport the state of this qubit to another qubit which is adjacent to the qubit between which you want to perform a coupling operation, and then you can perform a controlled operation. Then you might have to swap state with something else as well. So this swapping of states between qubits or transforming of states from one qubit to another qubit, this is genuinely required and routinely implemented on quantum computing chips. And this is happening on a single chip, because physically it may not be possible to link each qubit over there, but in an algorithm people might be wanting to have some joint operation between qubits at different physical locations. So that's why this teleportation is actually a necessity to implement general quantum computing algorithms on a quantum computer. So the second reason for this teleportation is actually communication, that you might have some quantum information on your quantum system over here, let's say in Lahore, and you want to send this quantum information to somebody in Islamabad. Okay, so somehow you might have access to a quantum channel, for example, some fiber optic, and maybe you're physically taking this system over there, and you want to then read this state and copy it somewhere in your circuit. So that's why we need this teleportation. And there is one big trouble in quantum mechanical system which comes from no cloning theorem. And this no cloning theorem which I'm not going into, proving it, states that if you have a quantum mechanical system in some general state psi, you cannot, copy this state to another state with to another system without destroying it. So that's what we will see also when we work it out, that when we read the state of quantum system from here, its state is going to be destroyed. So the state is gone from here and transported to another part. Because of no cloning theorem, we cannot have a copy of the state to another place and then a copy left at the previous place as well. So that state, would be destroyed. Okay, so after this, sort of lecture on the importance of this teleportation, let's now discuss how we can accomplish this. And first, let me give you the circuit for teleportation, and then I will give you the rationale for this circuit. And then you will see that I have another problem in the homework where you will be doing a similar analysis and coming up with a slightly different circuit for teleportation. Okay, so the circuit is like this. That suppose you have a third party which has prepared a Bell state of 2 qubits, and you have those 2 qubits, let's say this physical qubit. So you have access to this Bell state psi 00. This psi 00 state, just to recall, is a state like this. Okay, so suppose you already have 2 qubits in this state for this algorithm, and you already know how, if you don't have those 2 qubits in a Bell state, you know how to prepare them, right? In the last lecture, we studied that if you have a qubit in 0 state, another qubit in 0 state, but you perform a Hadamard on the first one, and then you perform a controlled X on the second one, with respect to the first one, you can get a psi 00 state. So we already know how to prepare this entangled state. So for now, we assume that this state has been prepared. Okay, so let me erase this part. Okay, so we have these 2 qubits that are prepared in this Bell state. And then there is this third qubit, which is in some state phi. Let's say this is qubit S. These are my qubits A and B. So I want to transport or teleport the state of this qubit to this qubit B. So the circuit is that I perform a controlled X operation between this first qubit and one of the entangled qubit, and then I perform a Hadamard on the first qubit. Essentially, this is, this part is measuring in the Bell basis, and then I measure this one. So let's measure this one, and let's say I get some I, and then I measure this thing and I get something, J. And then for this qubit, I perform an X gate controlled by this Jth result, and then I perform a Z gate controlled by this I result, and then I claim that the state of this qubit is the same as the state of this first qubit. And of course, during these measurements, this state would have been destroyed. Now, this is a protocol that I have drawn if you want to send, the classical information to somebody else, and that somebody else already possessed this qubit B, and then it can, prepare or transform this qubit B in state phi. Okay, so this is the circuit as I have drawn it right now, is essentially not for quantum computing, but for quantum communication. Because if I want to transport this state phi to a third party, what I first do is that I prepare 2, qubit in entangled state, keep one qubit to myself and give the other qubit to that third party, and that third party, is storing it somewhere, that qubit. And whenever later, at a later time, I want to transport some state phi, I, do these operations with uh, my qubit A, and then send these result I and J over classical channels to that person, and that the person perform an X control X gate with respect to J, which means that if J is 0, does nothing. If J is 1, does X gate first, and then look at the I bit, classical bit, and then if I is 0, does nothing. If I is 1, perform Z gate, and that person will have the state phi with him or her. But if we are working in on a quantum chip, we don't have to perform these measurements. And what I can do is this, and this is actually another principle, which is the principle of deferred uh, measurements, that I can defer the measurement and the control part. And instead of, measuring this, I can just perform the control operation simply with respect to this bit. And instead of measuring this, I can just perform the operation with respect to this, this qubit. So this is, more like the circuit if you want to teleport the state on a quantum chip while you are doing quantum computing, because you don't have to, first measure these two qubits and then send the classical bits to someplace else, and then that person performs these control operation, because you are just sitting right over there. You can just perform, these XZ gates right through the quantum control of these qubits. Okay, so this is the circuit, and let's see if the circuit works as I claim it to be. And for that, we will have a chance, to practice our Dirac notation skills now as well. So usually, whenever we have an algorithm, it's best, it's easier to analyze it in this fashion, that you first start at the input and see what is the state of the qubits. So at the input, I have this state phi, and this is for qubit S. And then I have this state 0, 0 of qubits A and B. And then now this is the state at the input stage. Let's now see what is the, so I can call it some, some state Q. So this is Q. Let's see what is the state after the control not operation. So after control not operation, I can work out this state, but before that, let me write it, this Q state in an explicit fashion. And for that, this phi S state, I can imagine that this phi S state is some alpha 0 and some beta 1. So this is a general state where alpha beta just have to satisfy this restriction. But otherwise, alpha and beta could be anything. So this is my phi state, and psi AB is already given. So this Q state is alpha 0, beta 1. For the moment, I'm skipping this S, but later on I will bring this S back. But you have to remember that this is the S state. And this phi psi 0, 0 entangled state is this 0, 0 plus 1, 1. Now let's prepare the product state. So I can take this 1 over square root 2 common. So this alpha 0 is tensored with both of these states. When this 0 is tensored with this, I get alpha 0, 0, 0, where the leftmost is the S qubit, then A qubit, and then B qubit. And then alpha 0, 1, 1, 0, 1, 1. I'm not writing SAB again and again. Plus beta 1, 0, 0 plus beta 1, 1, 1. So this is my state after it is, it is still the initial state actually. I haven't even gone to the next step. And before I even go to the next step, let me do a trick on this state. Okay. And the trick is that I multiply it with 2 and divide by 2. So I putting 2 here, and then I'm multiplying this one with 2. And after multiplying, I'm just writing it twice. So this is, and then this one. Okay, let's write this alpha 0, 0 here. Okay, and then I have this alpha 0, 1, 1, and I multiply it 2, but instead of writing 2 with it, I write it twice, 0, 1, 1. Similarly, for this beta 1, 0, 0, this is plus beta 1, 0, 0 plus beta 1, 0, 0 and plus beta 1, 1, 1 plus beta 1, 1. And you will actually see the rationale when we get to the result, that how we thought of this thing. Okay, so let me add plus alpha 1, 1, 0 here. And I'm doing these addition and subtraction because if you see at the circle what I want this B qubit to go to this state phi, which was at the S qubit. So somehow I will try to do the operation that on the right side, I have something that looks like phi, so that, I can take it common. So when I add this alpha, this, this is 0 on the right and this has 0 on the right. So I will be able to take alpha 0 common. So since I have added this alpha, I need to subtract it, and I subtract it from the second result, and still I have 0 on the right side. So I'll be able to take it common. So for here, let's me add beta 0, 1, 0 and subtract beta 0, 1, 0. And now the reason is this, that this is 0 on the right, so I'm adding 0 on the right. But since on the left, I will be left with this state 1, 0. But if I'm, trying to get the entangled Bell state, 1, 0 has to go with 0, 1. So that's why I'm adding a state beta 0, 1, and I'm subtracting the state beta 0, 1, this one. Similarly here, let me add alpha 1, 0, 1, and now you see the idea. This is 0, 1 on the left, so I'm adding 1, 0, so that when I take 1 common, I have a combination 0, 1 plus 1, 0. Similarly, let's subtract alpha 1, 0, 1. So over here, beta 0, 0, 1, because this is 1, 1, I'm adding 0, 0, and then subtracting beta 0, 0, 1. Now, let me take things common. So over here, I can take 0, 0 plus 1, 1 on this side, and alpha 0 will be common. And similarly, from this thing, I see that this is also a state 1, 1 plus 0, 0, and with beta 1 common. So if I combine this and this, I get alpha 0 plus beta 1, right? So this 0, 0 plus 1, 1 and alpha 0 on the right is common. And in this term, I will have beta 1 on the right side common. So 0, 0 plus 1, 1 is on the left. Similarly, let's see here. This is 0, 0 and 0, 1. So alpha 0 is common on the right side. So I have 0, 0 minus 1, 1, and then alpha 0 on the right. So where else I have 0, 0 minus 1, 1? So I have over here. So it's 0, 0, but this is minus sign, and 1, 1 is with plus sign. So I can take minus beta 1 common. So this is minus beta 1. So with this term and this term, I get this. So similarly, let's first think about this. So this is 0, 1 plus 1, 0, and alpha 1 on the right would be common. And on the left is 0, 1 plus, no, minus 1, 0, and alpha 1 is common. What else has this form? So 0, 1 minus 1, 0. Okay, so this is 0, 1 minus 1, 0. So minus beta 0 is common. Plus, no, so this one is gone and this one is gone, and I'm left with only this state. This is 0, 1. Okay, so 0, 1 minus 1, 0. I think I have made an error. For this state 0, 1 minus 1, 0, I took alpha 1 common. So, okay, so this was already taken care of. Now I have this state is left 0, 1 plus 1, 0. So 0, 1 plus 1, 0, 0, 1 plus 1, 0. So let's say it was coming from here. So alpha 1 was common. And this is 1, 0 plus 0, 1. And beta 0 was common. So this was a plus sign. So now let's say this one. So 0, 1 minus 1, 0, 0, 1 minus 1, 0 into alpha 1. And over here it's 0, 1 minus 1, 0. So beta 0 would be common minus beta 0. So this is the state that is still input state. I'm just rearranging it into different ways. And now you see if I take 1 over under root 2 inside, so this is nothing but psi 0, 0 state into this state, which is nothing but phi state, right? But now it's coming under B, and this is coming on qubit SA, and there is a factor of half. So what is this state? This is 0, 0 minus 1, 1. So 0, 0 minus 1, 1 is psi 1, 0 state. And over here, let's see, this is alpha 0 minus beta 1. So this is as if the phi state has been operated on by Z gate, because when Z applies to phi, it flips the phase of 1. All right, so the next state is this 0, 1 plus 1, 0. So this 0, 1 plus 1, 0 is psi 1, 1 state. No, this is psi 0, 1 state. So this is psi 0, 1. And along with it is alpha 1, beta 1. So this is just the phi state with 1 and 0 flipped. So this is as if X gate has been applied to phi state. Now the last one, this one is psi 1, 1. And you see alpha 1 minus beta 0. So it is as if first a Z gate is applied to phi, and then an X gate is applied, because there's a minus sign with beta. So first Z gate was applied and 1 went to minus 1, and then an X gate was applied to this state. So this is just the rearrangement of our input state Q. And let's get back to the circuit. And now you see that this part, this is nothing but measurement in Bell basis. So when we transform our circuit from this part, our circuit will transform in this way, that the psi SA00 will go to 00 state. The psi SA10 will go to 10 state, because this is just the inverse of the entangling circuit that we studied last time. And this psi 01 will go to 01 with the X gate on phi, and psi 11 will go to 11 state on XZ phi. So this means now that if the input goes to 00, our B qubit is carrying phi state. So nothing should happen to this. If the input, if the output of the first two qubit is 1, 0, the B qubit is carrying Z into phi. So a Z gate should be applied to recover phi. So that's why you see that there's a Z gate with respect to the this one, and there's an X gate with respect to this A qubit. This is the S qubit. So this is SA when this is 0 and this is 1. This is 0 and this is 1. Let's see if it in the correct order. So this is 1 0. So this is the yes. So the first one is the S qubit and the second is A qubit. So this is when this is 1, Z gate will be applied to get Z square and we will recover phi and so on. So it means that when you have 0 0 on this qubits ij, you get phi b and you do nothing and you get phi. When your ij qubits are 1 0, it means your b qubit was carrying z phi b. So you apply z to get z square and you get phi again. If your ij qubit are carrying 0 1, it means your b qubit was carrying x phi. So you apply another x. So this x is to be controlled by this qubit a, because this is SA. So you get phi. And if your ij are 1 1, your third qubit b was carrying xz phi, which means that you should first apply an x and then apply an z on your xz phi so that you recover phi, because x square I then z square I. So you apply x. So you're getting xz. Sorry, this is xz. So you have to apply zx. So zx. So it means that the z gate is based on this one, and the x gate has to be conditioned on this right most qubit. So that's why this circuit that you see over here. Okay, so you see how this circuit can transform the state from this to this part. Any question regarding this?
सर आप ऊपर की कैलकुलेशन थोड़ी देर के लिए दिखा सकते हो जो आपने 2 से डिवाइड और मल्टीप्लाई किया था उस वाले से.
Okay, just a moment. So right here. So this was, the tricky step, that when I went from here to here, first I, multiplied with 2 here and divided by 2. And that 2 I took inside, and this first term, which was twice, I wrote it twice. Instead of, keeping 2, I wrote it here and here. And then this term, I wrote it here and here, and similarly the other one. And then I subtracted these terms to keep the equation, that whatever I added, I subtracted, but in a way that I could, make the left 2 qubits into an entangled state, and I could take the right qubit common. And then I combined, the similar terms. So this 0 0 1 1 was common here, and 0 0 and 1 1 was common here. So then I combined this beta 1 and alpha 0 and so on. And then once you have this state, it's now just a matter of our knowledge that we know that if we have a Bell state, we can write the inverse of the Bell circuit, and that will convert this Bell state to this index state, whatever the index is, and then based on those index we can work out the gates that we have to apply to the third qubit to transform it into phi b.
Okay, sir. Thank you.
Okay, excellent. So any other question? If not, let me quickly show the circuit for teleportation on Jupyter. So Okay, so let me, this time instead of writing the code, I'm going to show the code, and I'll upload the notebook there as well. Okay, so you see this is the notebook that implements this circuit. So in the first part over here, I just have the usual things where I'm importing quantum circuits, plot state, Q sphere, state vector, and then this air, execute, and basic air. So let me run this. Okay, so there's a star here. So once this is run, here I have this circuit. And let me describe this circuit. So the first thing is that I have this import numpy as np, but then I have this column vector that I have prepared. The first one is my A, and the second one is my B, so that I can initialize this TC1 circuit, the 0th qubit, with this state phi. So this is how you can arbitrarily initialize. So I called a circuit with the 3 quantum bit and 1 classical bit. So this TC1 is my circuit, and I'm initializing the 0th qubit with this state phi. As you can see that this Q0 is now arbitrarily initialized. You do see that it's written 0.83 here and 0.54, simply because this term is not 0.7. This is the square root of 0.7, and this is the square root of 0.3. And I defined it in this way because I need to make sure that my A square plus B square is 1. So if I define it through square root, I know 0.7 plus 0.3 is 1. So their square roots square will be 1. Anyway, so now I have initialized this Q0 here. And then I just put this barrier for visualization part. And now you see this first part, Hadamard and CX, this is just preparing a size 00 state between qubit 1 and qubit 2. Okay, so this is the part that we just assumed in our analysis, that we have an entangled state shared between state qubit A and B. So this is where I'm preparing it. And once I have this, I just put this artificial barrier for visualization. And then this is just the inverse of this entangling circuit, which is the part of our entangling algorithm. And then you see that I have implemented this CX gate, which is just the control X gate with respect to the second qubit. And then I wanted a control Z gate. But just to show you guys, I'm not implementing control Z gate. I'm implementing control Z using control X gate, because Hadamard is actually Z gate. I think we did an activity yesterday on this, right? Where you showed Hadamard X, Hadamard is Z.
Yes, sir.
So here, okay, so here you can see the applicability, that if your hardware doesn't allow controlled Z gate, you can implement controlled Z gate using controlled X gate like this. So this is just that implementation. So let me run this circuit. And now this is just a way to visualize this thing. So you can see that this state phi, which was on this qubit Q0, once you evolve using state vector simulator, this is the qubit number 2 is gone to this state phi, and the first 2 qubits because of these operations, they have gone to the state 00. So let me run it again, and you see this here. And you can see the plot of output vector. And this is just a way that you can visualize these states on Q spheres. But when you have too many outputs, too many terms in the output, it's not always very helpful. Okay, now I'm drawing the same circuit again, but now I have used this measurement gate at the end, and now I simulate it using COSP simulator. And you see that if I simulate it using the simulator, I am having this probability distribution that my 0 has this probability 0.7 and my 1 has this probability 0.3, which is almost the same as the state that we specified. So let's increase the number of shots to higher term to increase the accuracy. So with this 10,000 shots, let's make it 100,000. And you see the accuracy increases. So let's make it actually 1 million. Might have to wait a little bit. But while we are waiting on this, okay, now you see that with 1 million runs, we are able to get a probability distribution that, you know, tells us that the state is really phi. You know, don't confuse this thing that the state transferred here was not phi. The state was phi, but our measurement only gives us partial picture of the state. So that's why we have to repeat experiment many times to really see what was the state out here. So by doing 1 million, 1 million time these measurements, we are able to sort of approximate the state better. Any question regarding entanglement?
सर एक जनरल क्वेश्चन था, मल्टीपल एक्सपेरिमेंट्स करने से आपकी एनर्जी जो कंजम्पशन है वो ज़्यादा नहीं होगी?
बिल्कुल होगी.
ज़्यादा एक्यूरेसी के लिए you need more energy.
Yes, yes, you're absolutely right. So you see, this is also one of the great research direction, and a lot of people are frantically working to come up with measurement strategies that you need to run, you know, fewer time. You need to run the circuit fewer time and still get a better, you know, estimate of the state. So this is called state tomography, and this is one of the active area of research, coming up with, you know, novel algorithms of running the circuit with the smaller number of times to still be able to, you know, approximate the state to a higher accuracy. And by the way, there's a lot of, you know, work going on in these quantum computing building companies where efficient implementation at the assembly level is being figured out to implement all the, you know, required gates using the sets of gates that they can efficiently implement. So for example, these types of things, that how you can implement CZ in an efficient manner and so on. Okay, so before I close this session, I would just like to request you that before next week, please go on to IBM's quantum computer login page. This is quantumcomputing.ibm.com, and create your account and get an IBM ID. And once you have this account, you can log in here. Because so far we have run all of our circuits on you know, the local simulator, but from next week I would like to show you how you can run these circuits on IBM's quantum computer. So you need to get this profile made and activated, and then in the next class I will be showing how you can link the Jupyter notebook on your personal laptop to the quantum computer in the cloud in the, you know, IBM's facility. And after that, you know, it will be just this thing that you will run circuit over here, but the circuit will go to their facility, and after running this, the result will come back and they will be displayed here on your own computer, just like here. Okay, so let me close the recording.